The mathematics of quantum mechanics is, technically speaking, linear algebra in an infinite dimensional vector space. Now, if that seems a little bit unfamiliar, don't worry, we will work through it step by step. It does turn out, however, to be an immensely powerful mathematical structure. There's a lot more going on behind the scenes to quantum mechanics than simply the wave function. What we're really talking about, in terms of the formalism of quantum mechanics, is attempting to represent the quantum mechanical state of the system. Now, what is the state of the system? Well, quantum mechanically speaking, it's everything that we can possibly know about the physical system that we're working with. There is no further level of information than knowledge of the state. And we've been working with states in a couple of different ways. The first way we worked with state was this notion of a wave function. Let's say psi of x and t. And to some extent, you can write down sort of closed form mathematical expressions for psi. Let's say psi is equal to some sort of, maybe it's a Gaussian, or a sinusoid, or a complex exponential. We also thought about representing the state of the system as a superposition, a sum over n of some coefficient a sub n, multiplied by some psi sub n of x and t, where these psi sub n's come from solutions to the time-independent Schrödinger equation. We're talking about, say, particle in a box, or the quantum harmonic oscillator. Gives you sets of wave functions that you can superpose together to represent an arbitrary state of a quantum mechanical system. We also talked about representing the wave function as some sort of an integral. Perhaps we're integrating from minus infinity to infinity. Instead of summing, we're computing an integral. We're integrating perhaps decay, if we're working with the free particle, for instance. And we have some sort of a phi of k, some sort of a coefficient, that tells you how much each of the stationary states for the free particle that we have to work with. And those free particle states look something like e to the I kx minus h bar k squared over 2m t. And there was a normalization divided by the square root of 2 pi, if I recall correctly. Now these expressions bear a certain similarity. Instead of a sum, we have an integral. Instead of a discrete list of coefficients, we have a function, phi of k. And instead of a stationary state, we have a stationary state. We also talked above and beyond these sorts of representations, hinting at some sort of a deeper mathematical structure. We wrote down expressions like psi sub n is equal to a plus the operator acting on psi sub n minus 1, all divided by the square root of n. This sort of expression came from a consideration of an operator algebra that actually had no knowledge whatsoever of the states. So while you can think of representing the states as sort of a closed form mathematical function, some sort of a list of coefficients, some sort of a function, there's actually more going on behind the scenes. We also have this notion of operators relating different states to each other, and these expressions are going to be true regardless of the nature of psi 1 or psi n and psi n minus 1. That expression has to hold. Why? Well, there is a deep mathematical structure going on behind the scenes here. So let's explore that mathematical structure. That's what this chapter is all about. So, what we're working with here, like I said at the beginning, technically speaking, is linear algebra in Hilbert space. Now, if you've studied linear algebra, you know it deals a lot with vectors, and you can gain a lot of intuition about the behavior of physical systems in terms of vectors. So, say we have some sort of a vector A pointing in that direction, some sort of a vector B pointing in that direction. You can do basic vector operations on these things. We can, for instance, take the dot product of A and B. And I've drawn these things as approximately perpendicular to each other, so you would expect the dot product to maybe be 0. We can also write perhaps the vector B as some sort of linear transformation acting on a vector A. And in the language of three-dimensional vectors, it's easy to write down linear transformations as matrices, in this case 3 by 3 matrices. So if you've studied linear algebra, these sorts of concepts are familiar to you. In particular, there are a lot of linear algebra concepts, things like the inner product or normalization or orthogonality and the notion of a basis that we can express. Now, the nuance in quantum mechanics is that we're working with a Hilbert space. And a Hilbert space, technically speaking, is an infinite dimensional vector space. So the infinite dimensionality here, I think I've actually written infinite, but you get the idea. Instead of working in 3 dimensions, we're working in infinite dimensions. Instead of lists of 3 numbers, we need lists of infinitely many numbers. And that makes life a little bit more difficult. The basic structure ends up being the same, though, so much of your linear algebra experience is still going to hold here. To give you some basic vocabulary and some basic intuition, we're dealing with vectors, first of all. And the notation that we'll use for a vector in the notion of a vector in this Hilbert space is going to be something like this. So vertical bar, name of vector, and then angle bracket. We'll expand on this notation much more later on in the chapter, but for now, just think of this vector as somehow representing the state of the system. As a proxy, think something like psi of x, if you need a more concrete representation of the state. You don't want to just think in general. Now, I contend that when we're talking about linear algebra and Hilbert space as applied to quantum mechanics, this representation is actually more useful than the wave function, and we'll see why that's the case later on. Oftentimes, we don't need to know anything about the wave function to still make useful conclusions on the basis of the vectors themselves. So what else can we do in terms of linear algebra? Well, we can do inner products. The way we'll write that in this notation is BA, or beta alpha here, angle bracket beta, vertical bar, alpha, angle bracket. In the language of states and wave functions, you can represent inner products like this as integrals, minus infinity to infinity, of, in this case, let's say psi beta star as a function of x times psi alpha of x, all integrated to dx. This is that same sort of normalization and orthogonality integral that we've been dealing with a lot in the context of wave functions, but expressed in a more compact notation, in a more general mathematical form, that of linear algebra. With this notion for an inner product, we can also think about normalization. Something like the vector alpha inner product with the vector alpha would translate into wave function language as an integral from minus infinity to infinity of psi sub alpha of x, psi sub alpha of x, need to complex conjugate this one, sorry about that, dx. And in terms of normalization, this had better equal 1, and this had better equal 1. So the inner product of a vector in this Hilbert space with itself had better give you 1 if this is going to represent a valid quantum mechanical state, same as the wave function has to integrate in this squared modulus context to give you 1. We can also talk about orthogonality. Orthogonality, in the language of linear algebra, refers to the vectors being perpendicular to each other if you're just thinking in 3 dimensions. Now, in infinite dimensions, it's a little bit harder to express, a little bit harder to think about, but it's just as easy to write down. I can say alpha and beta equals 0. That means these vectors are orthogonal to each other. In the language of integrals here, integral from minus infinity to infinity of psi alpha of x, complex conjugate, psi beta of x is going to give you 0. If these come from, for instance, a solution to the time-independent Schrödinger equation, perhaps we have a set of wave functions to work with. I'll write that as a set of states, say psi sub n. I may be guaranteed that psi sub n inner product with psi sub m gives me a Kronecker delta. This would express orthonormality, that this set is every element in this set is orthogonal with every other element, and that each element of the set is properly normalized. We can also talk about the completeness of a basis. So, working with this sort of set psi n, suppose it comes from solving the Schrödinger equation in the language of the wave function, I can express some arbitrary psi, arbitrary quantum mechanical state, as a sum of, let's say, n equals 1 to infinity potentially, of a sub n, psi sub n. If this sort of expression is possible, these psi sub n's form a complete basis. And if you think about invoking the orthogonality and applying Fourier's trick to this sort of expression, that works out just as well. You can figure out that in this case a sub n is going to be what you get if you take the inner product of psi sub n with this arbitrary wave function that we're starting with. Now these expressions have corresponding versions in terms of the wave function as well, but since I'm running out of space on the slide, I'm not going to go into the details. This one is going to be an inner product, same sort of integral as we're working with here. Likewise, this is your infinite sum. I think I had that expression on the last slide. Now, within the language of linear algebra and Hilbert space, we have this sort of notation, these sorts of representations for what these states really are as they exist in the vector space, or in the Hilbert space. What can we do with these states? Well, the fundamental question in quantum mechanics generally has to do with the observable properties of a system. So what do we have in the language of observables? Well, observables we know are going to be real numbers and they have some sort of statistical properties in quantum mechanics. For instance, we talked about the expectation value. Say I have some sort of observable Q, I can write the expectation value as Q inside a pair of angle brackets. And the angle brackets here are not exactly the same as the angle brackets in the earlier expressions that we've been working with, but the connection is, there is a connection. We'll come back to that later. If you want to think about the expectation value, for example, in terms of some sort of quantum mechanical system, we're dealing with an operator. So the observable isn't just going to be the expectation value of some Q, some quantity Q. We've got some sort of an operator, which I'll write as capital Q with a hat. So what would our expectation value Q look like in this language of angle brackets? Well, we know what it looks like in terms of inner products, or in terms of integrals of wave functions, for example. It's going to be an integral of the wave function, the state of the system, then the operator, then the wave function of the state of the system. And we have that same sort of notation in context of inner products in our vector space. So we would have the state of our system, psi, and we have our operator acting on psi. So the operator acting on psi gives you, in some sense, another state of the system. It's not really another state of the system, though. It's more a vector in this Hilbert space. Operators here, if I think about this Q operator acting on the state of the system, is going to give you some new vector in your Hilbert space. Now, we know that this sort of expectation value quantity or concept has to result in some sort of a real number. So you can think about this as, what happens if I take the complex conjugate of this? Well, if you're thinking about psi, Q hat psi, complex conjugated, in the language of the integrals that we've been working with, this is going to be taking the complex conjugate of Q hat psi. So instead of being a psi star Q hat psi, it's going to be a Q hat psi star multiplied by psi inside the integral. And the same notation sort of holds here. Whenever you take the complex conjugate of an inner product like this in our Hilbert space, you swap the order of these things. Instead of the psi being on the left, the psi is on the right. And the Q hat psi on the right is on the left. So this notion of what appears on the left and what appears on the right is a useful way of keeping track of what's been complex conjugated. So Q hat psi psi in our revised notation here. Now this sort of substitution here, if this is going to be equal to the original expectation value of Q, right? The complex conjugate of the expectation value has to be equal to the expectation value itself if this is going to be a real number. This expression has to be equal to this expression. And the equality of two operator expressions in the language of linear algebra like this, essentially the operator can act on the left or the operator can act on the right. The operator behaves the same when acting on a complex conjugate of the state as it does on the state itself. Complex conjugate of state with operator gives you the same result. That is only going to be true if the operator here is Hermitian. And there's lots more that can be said about the notion of Hermitian operators, and we'll come back to that in further lectures. But for now, know that there's a lot of mathematical formalism that goes along with linear transformations, such as vectors to new vectors in the space, especially associated with Hermitian linear transformations. So as an example of the notion of a Hermitian operator and how that manifests itself in this context, think about the momentum operator. Is the momentum operator Hermitian? Well, if the momentum operator is Hermitian, we know that if I have some sort of a wave function f, the momentum operator acting on the wave function g has to be equal to the momentum operator acting on f, inner product with the wave function g. Sorry, I shouldn't say wave function, I should say state. State f, momentum operator g, momentum operator f, state g. These things should be equal to each other. So let's do some manipulations of the one on the left. And just since we have a large amount of machinery for working with the notion of states in terms of wave functions, let's express this in terms of wave functions. So our inner product in terms of the wave functions is going to be the integral from minus infinity to infinity of some wave function f, complex conjugated, as a function of x, multiplied by the momentum operator applied to our wave function g. And our momentum operator is minus I h bar, partial derivative, with respect to x. So this is acting on the function g of x, and we're integrating dx. Now this is an expression that looks a little bit difficult to work with. We have partial derivatives inside an integral, but whenever you see a derivative inside an integral, think integration by parts. So let's say I do integration by parts. I can define my variable u to be some sort of f complex conjugate, recognizing the part that I would like to differentiate. And the part that I would like to integrate would be, well, the part that's already been differentiated. So let's say dv is equal to partial g partial x, with the dx tacked on. So identifying this part as my v and this part as my u. You can pull the constants out front if you want. So this is going to give me du would be the partial derivative of f star partial x, and my v, when I integrate it, now it's the integral of a derivative, so fundamental theorem of calculus just gives me g. Integration by parts then says this whole thing is going to be equal to f star of x, g of x, evaluated at my boundary, minus infinity to infinity, minus the integral from minus infinity to infinity of these two guys, v du. So I have my partial f, partial x, and I have my g, and I'm integrating dx. Oops, forgot to, technically I should put a dx there in my integration by parts notation. So, as usual in quantum mechanics, we require these functions to be square integrable, meaning normalizable, meaning they have to go to 0 at infinity. So 0 at plus infinity, 0 at minus infinity, this term all by itself drops out. Oh, and I've got this coefficient overall that I should pull out front. So minus I h bar multiplies all of this. So I've got a minus I h bar and a minus. The minus I h bar and the minus are going to cancel out if you want to simplify this, and I'll have I h bar. Let me put that inside the integral. I h bar, I have a partial derivative of f star, partial x, and g, and I'm integrating dx. So we're almost there. This looks a lot like the momentum operator applied to the function f. So we've almost sort of closed the loop here. We've almost shown that p is Hermitian. What's missing here? Well, what's missing is the notion of this minus sign on the IH bar. This here itself is not exactly the momentum operator applied to f. But what we want actually isn't exactly the momentum operator applied to f. It's the momentum operator applied to f, but then acting on the left in this inner product notation, which means we have to take the complex conjugate. So if I really wanted to write this out, I would have to say this is the integral, put some limits on here, minus infinity to infinity of minus I h bar partial f partial x, all complex conjugated, multiplied by g integrated to dx. And now we've actually gotten back to this original expression. This here is the operator p acting on f, complex conjugated, inner product with the function g. So that's the end result. We have sort of demonstrated that our definition of minus I h bar partial g partial x here is indeed a Hermitian operator. And perhaps this goes a little bit of the way towards explaining why exactly you had a minus I h bar, or minus I, in the definition of the momentum operator. That minus I is a little bit perplexing at first, but it is required essentially by the notion that the momentum operator be Hermitian, by the notion that the expectation value of the momentum is always going to be a real number. As a further example of how we can manipulate these sorts of things in the language of formal linear algebra, let's think about a state with no uncertainty. What sort of quantum mechanical state would have no uncertainty? These things are also called determinate states, meaning you have some operator or some observable, let's say the observable q as represented by the operator q hat, and it has absolutely no uncertainty associated with it. There is a quantum mechanical state that has a definite value of some variable, some observable. Now, if you're thinking about something like position or momentum, you might be thinking along the lines of the uncertainty principle, and well, is that really possible? And the answer is probably not. The states of determinate position and determinate momentum tend to be a little bit poorly behaved, mathematically speaking. But in terms of energy, perhaps, you know states of determinate energy. They are the solutions to the time-independent Schrödinger equation. So there's certainly nothing wrong with that. In particular, I can write something like sigma q, the variance, sigma q squared, the uncertainty in a measurement of quantity q squared. And I can write that this quantity was, back when we were talking about variance and probability distributions, defined as the expectation value of the operator q minus the expectation of q. So the deviation of some observable from its mean squared. So the expected mean squared deviation, the mean squared deviation from the expected value. Now in our language of linear algebra here, we can write this out as psi on the left, and then q hat minus the expected value of q acting on psi on the right. Oh, and this is squared, of course. So I can expand out the square, let's say psi on the left, and then q hat minus expected value of q, q hat minus expected value of q twice, acting on psi. And this operator, if this is going to represent an observable, has to be Hermitian. So if q hat, the operator, is Hermitian, q, multiplication by a number here, the expected value of q, this is just going to be a number. It's also, of course, going to be Hermitian. Multiplication by a number is going to be a Hermitian operator. Doesn't matter if you do it on the wave function on the right or the wave function on the left. I can take this whole thing and apply it on the left, since this is a Hermitian operator. So if you make that sort of manipulation, you end up with, now on the left, I have q hat minus expectation of q acting on psi, and on the right, q hat minus expectation of q acting on psi. And if this whole thing is going to have zero uncertainty, what exactly does that mean? Well, if this whole inner product is going to turn out to be zero, then either psi equals zero, meaning my wave function is in some sense trivial. That's not terribly useful. If psi is not zero, then each individual piece here, this has to in some sense be equal to zero. Or this piece on the left has to be equal to zero. What that means, well, either left and right, these are very similar expressions. It means q hat minus the expected value of q. In terms of that as an operator acting on my state, that has to equal zero. And that's easily rearranged into q hat acting on the state equals the expected value of q multiplied by the state. This is just a number, it's not an operator. This here, this is an eigenvalue problem. And there is yet another massive set of linear algebra machinery dedicated to solving eigenvalue problems. We've already done some of them. For example, the Hamiltonian operator acting on the state of the system is the energy times the state of the system. This is our time-independent Schrödinger equation. This gave us the states of definite energies, and that's the same sort of framework as you got in here. So that's a taste of the sorts of things that we can represent and think about in the language of linear algebra as applied to quantum mechanics. We can express generalized states with no uncertainty and derive that they are going to be the states that are eigenstates of the linear operators that represent the observables. Now, we haven't really written down any linear operators in detail in the notation of linear algebra or really in quantum mechanics. We've only really got a few operators that we can work with, like Hamiltonian and position and momentum and whatnot. But this is hopefully I have at least convinced you that there's more to quantum mechanics than just dealing with the wave function, that we can do some interesting things with the linear algebra structure. So to check your understanding here, let's consider a set of states that you get, stationary states from the quantum harmonic oscillator. That means the solutions to the time-independent Schrödinger equation, which if you wanted to write it out in terms of operators and linear algebra, is h bar psi sub I, let's say psi n actually, is equal to En psi n. So that would give us this set of solutions here. So in terms of the language of linear algebra, some basic notational questions. And in terms of whether or not observable operators are Hermitian or not, think about why the operator x hat, the position operator, would be Hermitian. The mathematics of quantum mechanics is, technically speaking, linear algebra in an infinite dimensional vector space. Now, if that seems a little bit unfamiliar, don't worry, we will work through it step by step. It does turn out, however, to be an immensely powerful mathematical structure. There's a lot more going on behind the scenes to quantum mechanics than simply the wave function. What we're really talking about, in terms of the formalism of quantum mechanics, is attempting to represent the quantum mechanical state of the system. Now, what is the state of the system? Well, we're computing an integral, or integrating perhaps decay, if we're working with the free particle, for instance, and we have some sort of a phi of k, some sort of a coefficient, that tells you how much each of the stationary states for the free particle that we have to work with. And those free particle states look something like e to the I kx minus h bar k squared over 2m t, and there was a normalization divided by the square root of 2 pi, if I recall correctly. Now these expressions bear a certain similarity. Instead of a sum, we have an integral. Instead of a discrete list of coefficients, we have a function, phi of k. And instead of a stationary state, we have a stationary state. We also talked above and beyond these sorts of representations, hinting at some sort of a deeper mathematical structure. We wrote down expressions like psi sub n is equal to a plus the operator, acting on psi sub n minus 1, all divided by the square root of n. This sort of expression came from a consideration of an operator algebra that actually had no knowledge whatsoever of the states. So while you can think of representing the states as sort of a closed-form mathematical function, quantum mechanically speaking, it's everything that we can possibly know about the physical system that we're working with. There is no further level of information than knowledge of the state. And we've been working with states in a couple of different ways. The first way we worked with state was this notion of a wave function. Let's say psi of x and t. And to some extent, you can write down sort of closed-form mathematical expressions for psi. Let's say psi is equal to some sort of, maybe it's a Gaussian, or a sinusoid, or a complex exponential. We also thought about representing the state of the system as a superposition, a sum over n of some coefficient a sub n, multiplied by some psi sub n of x and t, where these psi sub n's come from solutions to the time-independent Schrödinger equation. We're talking about, say, particle in a box, or the quantum harmonic oscillator. Gives you sets of wave functions that you can superpose together to represent an arbitrary state of a quantum mechanical system. We also talked about representing the wave function as some sort of an integral. Perhaps we're integrating from minus infinity to infinity instead of some